The rainbows look like this when their pictures are taken, but those little lines tell the metallurgists a big story. Each of the lines means something. In this instrument, they're examined and their density noted. By accurately measuring the density of the lines, the exact amount of the metal in the alloy is determined. Just 8 minutes from the time the sample is received, a report on it is back at the foundry. The report may call for the addition of some element needed to keep the proportions of each metal in the alloy correct. This saving of time ensures quality. In addition to the big main laboratories, there are a dozen smaller laboratories scattered through the plant. The big labs establish the standards of quality, but these standards aren't left to enforce themselves. They're carried out by men in these special laboratories located right where the glass or steel or tires are being made. The workout Junior here is giving this teething ring is, as you see, child's play compared with the systematic tests given samples of the 200 rubber parts that go into each car. On test are fan belts, tires, tubing, and body mountings. All vital engine parts, not just occasional samples, but all of them, are gauged in rooms like these, near the point of production. The gauges are very accurate, and to make certain they stay that way, the rooms are air-conditioned. Otherwise, changes in temperature might affect their precision. Ford gauges take many forms, and some are very ingenious mechanisms. For example, this piston pin inspection machine, developed and built by the Henry Ford Trade School, is sensitive to differences as little as 25 millionths of an inch. It automatically gauges and sorts 2,250 piston pins per hour. This machine also checks each pin for hardness, roundness, length, finish, absence of taper, and diameter, then sorts the pins into a 5-compartment container according to size. Without this machine, it would not be practicable to examine every piston pin with such care. Timing of amazing accuracy and grace makes this circus act an outstanding success with the crowds. Precise timing is of top importance in an engine, too. And for that reason, camshafts must be made just right. This camshaft inspection machine, also designed and built in the plant, checks every measurement on every camshaft automatically. On the high wire, balance of the most delicate kind is needed, and these star performers have what it takes as they go through their daring routine. Balance is also one of the prime factors in a crankshaft. In this room, crankshafts are checked for both static and dynamic balance on these machines. Even the weight of a thin dime would throw the crankshaft out of balance. To ensure that every valve seat insert is perfect, all of them are subjected to an unusual test. A good ping pong ball bounces well, but a bad one won't. So it's easy to find and throw out the bad ones. Much the same method is used in testing valve seat inserts in this machine. Perfect rings bounce into the container, but those not up to specifications for hardness and solidity can't bounce high enough, and so fall into the container for rejected rings. The machine also discards odd-sized rings. More than 38,000 precision gauges are in regular use in the production departments of the Rouge plant. Many of them are accurate to within 1/10,000th of an inch. To make sure that they stay accurate on the job, they're checked with Master Johansson gauge blocks. These blocks are recognized as the world's standard of measurement. Production gauges, the gauges employed right in the shop, are checked against them at least once a day. Tested materials are made into tested parts, and the parts are made into the finished car on these assembly lines. But Ford testing methods go beyond tests of materials and parts. At regular intervals, a car is taken off the production lines to go to destruction for the sake of science. For these doomed cars, there's a whole series of tests on the test tracks and in the new weather tunnel. A car is driven into the tunnel where weather equal to the world's worst of Arctic tundra and tropic desert, of mountaintop and seacoast is made to order. The car goes on a treadmill, and the man at the controls speeds up the engine until the rear wheels are spinning near top speed. Then he opens the sleet-making mechanism and turns on the big propeller. The temperature drops to 0, and ice quickly coats the car, while the wind velocity rises to 70 miles an hour. What a storm this is, and what a test of car stamina. For hour after hour, the car runs on, while engineers tabulate the data brought them by nearly 100 recording instruments. Then the temperature may be sent abruptly upward. Instead of an Arctic storm, suddenly we have the scorching heat of the Sahara in summer. Humidity goes down. The load of the treadmill is increased to imitate the dragging action of deep desert sand. Still the car rolls on. Then, without moving an inch, the car is transported from desert to mountaintop. How? By reducing the air pressure until it duplicates the rarefied atmospheric condition of a lofty peak. Still another turn of the controls, and dust and sandstorms may be hurled in turn against the car before it is drenched in torrential tropical rains such as we see here. In short, almost every conceivable type of weather can be produced in this tunnel. The purpose, of course, is to find out promptly how newly designed cars will perform under every condition. To find out now without being obliged to wait for reports from test cars in remote parts of the world. And now for an idea of what all this varied research means to the car owner. For many hours, this car stood in the tunnel in a temperature of 20 degrees below zero. But it starts almost instantly and is backed out of the tunnel. Without a moment for this chilled mechanism to adjust itself to the abrupt change, it is driven onto the test track. It never falters, never misses fire, as the driver, peering out of the tiny cleared patch on the windshield, speeds around the track. The tunnel also is valuable for research in body design. Cars are suspended in aerodynamic balance and tested in an air stream from the big three-bladed propeller to discover the amount of air resistance or drag they present at various speeds. These tests also show the gain in slipstream efficiency, made possible by changes in the contour of bodies and body fittings. This data helps the designers make cars that are more efficient and more economical. In addition to tests of the performance of the entire car, the efficiency of batteries, radiators, insulation, and other factors is tested in a special cold chamber where the temperature may be sent down to 40 degrees below zero. Dressed like a polar explorer, the research man goes steadily forward with his experiments, telephoning the results of each to his colleague stationed outside the observation window. Restful quiet in a car, even if it is traveling fast over brick roads, is one of the things demanded of the modern automobile. Some clever equipment was developed to let the engineers find out just what makes sounds, how they get into the car, and how to damp them out or silence them altogether. Road tests, in which sounds are measured at all speeds from 20 to 70 miles per hour, are conducted over many different kinds of road surfaces. Engineers equipped with sound level meter, stethoscope, microphones, vibration analyzer, and other special instruments trace down all disturbing noises. Sometimes the work of hunting noises leads to unexpected places, such as the luggage compartment. Armed with accurate information, the designers develop car bodies that bring a new quietness to motoring. Cars are tested on this track. The high-speed section, the gravel, cobblestone, Belgian block, and other sections provide information on performance and safety factors in the cars. The tests go on all the time, day and night, summer and winter. By far, the most formidable part of the test track is the torture section, a 1/3 mile stretch of concrete mounds in a staggered double line. One test of the springs and shock absorbers requires the car to be driven over a single row of mounds in a terrific bouncing action. And then, with the car traveling at 40 miles an hour down the center, comes another test just as bad. If there is any possibility of any part of the frame or any of the body mountings working loose in thousands of miles of normal service, the engineers find it right here. Science in the automobile industry advances on a score of fronts. The tests and research methods of the Ford Motor Company, which we have just seen, are only a few of the more outstanding developments which have helped make the American motor car a worldwide symbol of efficiency and value. Seeing them, however, may help bring a wider realization of the thought and work a great industry puts into its endless effort to bring greater safety, value, and comfort to modern travel.